Okay, so I'm recording the theory notes from this point on, and they will be uploaded onto Google Classroom along with this PDF at the end. So if you get a little bit behind in the note taking, don't worry, we'll get there. So there's the success criteria as I just chatted to the class about, and now we're on looking at slide 3 and the general form of the exponential function. So probably don't bother writing the notes down there unless you think that's useful for you to see. But so the exponential function looks like this: y is equal to k, okay, and k is just a constant value, multiplied by a to the power of x, which typically gets put in brackets, that value there. Okay, so again, what makes an exponential function an exponential function is the fact that the variable is the power. You know, for a quadratic, it'd be x to the power of 2. Okay, so the variable is not the power because 2 is constant, but the constants are down here and it's the power that's variable. And that's what gives it its extraordinary growth, because as x increases, then the power increases. And as we raise something to a higher power, it gets bigger and bigger very quickly. And there's a couple of conditions where k is greater than, k is not equal to 0. And I'm hoping that kind of makes sense, because if k was equal to 0, then you just have y equals 0. So it's not because you can't do it, it's just because it's boring. And the other value is that a must be greater than 0. Now, technically, you could have a less than 0, but what happens is, because of the way powers work, and because x can be even and odd, and if you think about raising a negative number to an even power and raising a negative number to an odd power, what happens is that when a is less than 0, when a is negative, it becomes sort of unpredictable in the way its shape is formed. And so we tend to just not bother with those kinds of functions. There's nothing predictable. They're not predictable enough to be useful. So we set a to be greater than 0. And there's a little note down the very bottom there which says transformations are covered in Maths Extended. So we're going to stick to, there is a little transformation here. K is actually a transformation. It really should be. The parent graph is actually y equals a to the power of x. So transformations like, 3 times 2 to the power of 6x minus 1 plus 4, that's a transformation of this basic graph. And you will cover it in Maths Extended, but not in this part of the course. Okay, so now we're going to have a look at the different parts of the exponential function just to unpack what they do. So I'm looking at slide 4 now, and that value k is often called the initial value. So in our population example from the last lesson, the starting population was 24 million. And that was the value of k in the function when we created it. So you can write it for yourself, but I'll just read what it says. Exponential functions are often described in terms of time, thus making when x equals 0, given that x is the variable representing time, when x equals 0, the start of the time period. Okay, when x equals 0, it's the start of the time period. So if I have y, now I've just deliberately kept it in general terms. I don't care what k and a is at this stage, other than k not being equal to 0 and a being greater than 0. So when I let x equal to 0, let's just see what happens. We've got y equals k times a to the power of x, which is equal to k times a to the power of 0 at the start, right? The initial value of x is 0. And anything raised to the power of 0 is 1. So that means I'm going to spell it out here, k times 1, which is equal to k. So you can see that when x equals 0, the initial value of the function must be k, which is why we call the initial value k. P.S., and we're going to have a look at that on the next slide, that also makes k the y-intercept. Because remember, the y-intercept is when x equals 0. I'm going to move slides in a second, so I'm just going to give you a moment to finish writing that down for those who are a little bit slower. Not too long though, so again, you can catch up with the notes online, but ask questions now as well if you're not too sure about anything. I don't care what the question is. Well, I do a little bit. But if it's something that's relevant to what we're doing now, ask it now, or forever hold your pieces. Okay, so next slide set. The second thing to consider is the shape of the graph. Now, on the whiteboard, so we can't see it here on the air sketch show here, but on the whiteboard, you can see what the kind of shapes are that we're looking at for an exponential graph. We're going to draw them in a second. But what makes the shape, what determines that shape, sorry, is the value of A, okay? So there are a couple of conditions. First of all, I might even just zoom up so maybe we're just focusing on that bit there. We've got when A equals 1. Okay, so I'm just going to fill this table in and then we're going to unpack it a little bit further in the next few slides. So when A equals 1, we have the shape of it. It's called a static because it is neither growing nor decaying. But it's effectively a straight line. We'll see that in a second. Now, there's a bit of notation here that I just want to make sure you're okay with. When you see A and then surrounded by less than and greater than signs like it is here, it basically means A is in this range. So when you see 0 is less than A is less than 1, it simply means that A is a proper fraction, okay? So 2/3, a fifth, 0.97, whatever it is, A is a fraction. It is less than 1, but it is greater than 0. So when we have that happening, when A is a fraction, the shape of it is a decay graph. And when A is greater than 1, like we had in the population example from last lesson, it is an exponential growth graph. So it's static, it's exponential decay, or exponential growth. I'm going to zoom out now so you can see the other 3 slides, and I'm going to tackle each of these in turn as quickly as I can. Now, static is boring. We're not going to, it's not exponential, really. So I'm not going to spend too much time on it. But again, this just simply uses the idea that if y equals k times 1 to the power of x, so if I'm saying A is the value 1, then k times 1 to the power of x is simply going to be k, right? Because 1 to the power of anything is just 1. 1 to the power of 97 is 1 times 1 times 1 times 1, 97 times. It's just equal to 1. 1 to the power of a half is the square root of 1, and the square root of 1 is 1, etc. So it doesn't matter what we do. We raise 1 to that power, we get 1. So that means that y is just equal to k, a constant value, which means that if I were drawing it, it's very boring. K may be positive or negative, so this is just representative of it. If this is y and this is x, then the graph of the function would simply be something like this. Okay, where it cuts through the y-axis at k, and that's it. No growth, no decay, it's just sitting there. The next 2 are the ones where we want to focus our attention. That is exponential growth when A is greater than 1. So I'm going to put the summary notes into this into AirSketch, but I'll just do a little bit of explanatory work as we go along. And what you'll see here is that I've asked you to consider what happens as x approaches infinity and x approaches negative infinity. We know the basic shape of the exponential graph, but again, this is where we start considering what happens for values, for negative values of x as well as positive ones. So when you see x approaches infinity, that simply means what happens as x gets really large. Infinity is a concept, not a specific number. And when you see x approaches negative infinity, it simply means what happens with x as x gets really large, but in a negative direction. Now, in order to think, well, as x gets really large, if A is greater than 1, then as x gets really large, what's happening to y? Well, as x approaches infinity, y gets really big as well, doesn't it? Even bigger. So as x gets big, y gets big. And hence we have this sort of exponential growth happening. But as x approaches negative infinity, I want you to think about what that means. So we have taken a number and raised it to a negative power. Now, I want you to see if you can remember, okay, this rule here, which simply says that if I take a number and raise it to a negative power, it's equal to 1 over the number to a positive power. Does that ring a bell for people with their index laws? If not, the rule is if you've raised a number to a negative power, it's equal to 1 over a to the positive power. So what does that mean? That means that as x approaches negative infinity, a to the power of this negative number, let's just call it negative x for the time being, would be equal to 1 over a to the power of x. But now that x is positive, it means that a to the power of x is getting really big. A to the power of x, this is just scribble notes, so don't necessarily write them down. A to the power of x is going to get really, really, really big. And what's 1 over big equal to? Well, nothing specific, but as we make the denominator bigger and bigger and bigger, what happens to that fraction? Let's just think of a few just to get your mind thinking. A half, and then a quarter, and then an eighth, and then a 16th. All I'm doing is going up by a power of 2 here as a fraction. So a half, a quarter, an eighth, a 16th, 1 over 32, 1 over 64, and so on. What is happening to those values? Someone yelled it out before, but I prefer raised hands. Thomas, it's getting smaller and smaller and smaller. So if I went to 1 on 2 to the power of a 1 followed by that many zeros, this is the technical term for this fraction. This fraction is called really small. Yeah? Should it be in the K section? The decay section. No, it shouldn't be, and I'll explain why in a second. Oh, sorry, hello.
Mia? She's got the okay.
No.
That's right. Thank you.
Okay, so as x approaches, so what does this all mean? It means that as the bottom gets bigger and bigger and bigger, the fraction gets smaller and smaller and smaller, and so it approaches 0. But note, it never gets to 0. 1 over 2 to the power of a squintillion, zillion, dillion, brillion, zillion, dillion, billion, dillion is really close to 0, but it's not 0. So it approaches 0, but it never hits 0. I'm going to rub all that out. Okay. That means that when I'm drawing the graph, and this will answer your question, Jem. When I'm drawing the graph of an exponential growth, as x approach on this side of the graph, it's growing because y is approaching infinity. So we have like that. But as x approaches negative infinity, I didn't leave myself room, did I? Silly me. As x approaches negative infinity, y approaches but never reaches 0. So from the other side, we have this kind of thing happening. Okay, so I'm now going backwards on my graph to the left of the graph as x gets bigger but negative bigger. You know, have you talked like in physics or whatever about magnitude? Okay, so magnitude is like if you strip off the sign, the number itself is big. So like if you have $1 million, that's a big number. If you owe $1 million, that's a big number. One's positive, one's negative, but they're both big. So the magnitude of x is still big, but as if it's a negative number, it's approaching 0. If it's a positive number, it's growing that way instead. It's approaching infinity. Okay, does that kind of make sense? All right, so moving on to the next one, which is exponential decay, we've got exactly the opposite happening. So A is a fraction, right? So again, I'll just draw these notes in blue so you know they're not official notes as such. So if I have a fraction, if I say like A is equal to, let's say 1/3, for example, then as X approaches infinity, what we're doing is we're raising 1/3 to a really large number. Okay, like that. And that means a third times a third times a third times a third times blah, 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 blah. So I'm hoping you can see from that, that in this case, if A is a fraction to start with, then as X gets bigger, Y goes down towards 0. Okay, so we've got this sort of thing happening. As X approaches infinity, Y approaches 0. Okay, it also uses this rule as well, which I'll need in a second, and that is that if I have 1 over 3 to the power of x, that's the same as 1 over x over 3 to the power of x, which is 1 over 3 to the power of x. Okay, so again, as x gets bigger, 3 to the power of x gets larger, so 1 over that number gets really, really small. Okay, so what about as x approaches negative infinity? So let's again just do it by example so you can sort of see what I mean. If I had a half to the power of -1, then that would be 1 to the power of -1 over 2 to the power of -1, just distributing that -1 there. And 2 to the power of -1, I'm just hoping I'm hoping your maths, sorry, your index skills are coming back to you, means that that 2 to the power of -1 floats up here. And so the net result of that is 2 to the power of 1, which is 2. And again, I'll just take it a fair bit down the track now. Say a half to the power of -10 is 1 on 2 to the power of -10. The negative index floats up, and so we're left with 2 to the power of 10, which is equal to some number. Okay, so if it's a fraction to start with, raising a fraction to a negative power effectively flips the fraction and makes it bigger than 1, which therefore causes it to grow when x is negative. So the net result of all that is that as x approaches negative infinity, y approaches infinity. Y gets bigger as x goes down the left-hand side there. So what does that mean? That means, I'll just get rid of that so I can draw the graph. That means the graph for a growth graph, sorry, with the graph for a decay function, you can tell that I'm sick still, can't you? I'm even more vague than usual. Would look like this. We've got x and y here, and we would have the decay happening after the y-axis, so something like this, and it's approaching 0. And then before the y-axis, we have y growing as x gets negative, and so we would have like that. So it's basically the opposite of the opposite looking kind of graph. Notice in both instances, it cuts through the y-axis at k. Okay, so I'll draw that in for both of those so you can sort of see it. I'll just do it in blue so it sort of stands out. So that's the value of k there. And there, that's the value of k. So it cuts through at k, and that's the shape of it. Exponential growth, exponential decay. I'm going to move on to the next slide in a second, so I'm just giving you a chance to catch up there. If you've got any questions, do ask them. Jem? I can't hear you because people are being rude. Go again. No, in fact, if you think about it, there is no x-intercept. Because as x gets bigger and bigger and bigger and bigger, or smaller and smaller and smaller and smaller, it will approach the x-axis, but it will actually never cross it. Now, there are transformations which will make it cross, but for the basic exponential function, it approaches the x-intercept but never crosses it. However, k is the y-intercept, and that is because the y-intercept is when x is equal to 0, and hence the a to the power of x disappears or is equal to 1. Okay, I'm going to move on to the next slide. Sorry if this is going a bit too fast for some people's writing, but that's what the notes on Google Classroom are for. So we're now going to have a look at graphing. I'll do an example. I've written down the steps there. There's only 3 steps really. But I'll do, yeah, I'm sorry, they're out of order because I wrote them down and then realized I probably should have talked about shape first. So just write them down in the right order. It's 1, 2, and it's number 1 is the shape. Number 2 is the y-intercept, knowing that you don't have to worry about an x-intercept unless there's a transformation happening to your exponential graph. So 1 is the shape, 2 is the y-intercept, 3, because there's very little information about an exponential graph that really helps define it, like a turning point and stuff like that, then it's often advisable to graph one other point. So in this case, you choose one that's easy to do. So typically that's when x equals 1, because then it's pretty easy. So the example I've given you is y equals 10 to the power of 10 times 2 to the power of x. Okay, so I'm just going to go through those steps. So number 1 is the shape. So I have a look at a, which is greater than 1, therefore growth. Number 2, y-intercept. Let x equal 0. So that means therefore y is equal to 10. So that's 0, comma k effectively. And number 3, one other point. Let x equals 1. Therefore y equals 10 times 2 to the power of 1, which equals 20. So at 1, we've got the point 20. And I think I'll just do the graph just in that little bit of space off to the side, because I don't really want to waste too much room there. Okay, so we've got, it's a growth graph. So I think I'll just put my axes over here a little bit. There's y, there's x. Let me see now. Value of 10 here. And so value of 20 here. Now, I wouldn't bother trying to keep your x-axis in scale with your y-axis, because it'll just be really squishy. 1, 2, 3, that's all I need really. Don't even need the 2 and the 3 there. So there's 0.120 there. And then I'm just going to, now you can do it in one smooth motion if you want to, or if you otherwise just do it from the y-intercept. So sort of, I'm going to graph up there, and then I'm going to graph down there, like so. So I've labeled my axes. I've got my 2 critical points in, like so, which I'll label, and I'm basically done. And I've got it as a growth graph. So that's not too bad, is it? It's easier than a quadratic, really. It's just new. Okay, so in slide 11, this is from exercise 3J, page 213, question 4. You're going to finish off exercise 3J in a moment. I'm just going to go through part A, and then you're going to do B, C, and D, and E, or whatever you got time for in the rest of this lesson. So I'm going to give everyone a moment to get their textbooks open to page 213, and then I'll take you through this as an example. It's on the board there. I do need to move on. So if you don't have your textbook open, you're just going to be a little bit behind, but it's on the board anyway. So this is just an example of a real world modeling problem. It's not a terribly hard one. So it's just, it's just there to understand what we have to do. So question 4A says, a flat is purchased for $200,000 and is expected to grow in value by 17% per annum. That's what the PA stands for, per annum. Now, what it will ask you to do in question 4 is, I think, just come up with the function. Yep. Whereas I actually want you to sketch it as well. Now, the textbook won't have the sketches drawn in, but I want you to sketch it, and then I want you to use Desmos to confirm. Okay, so here we go. So basically, in order to solve this problem, we simply need to identify the values of K and the values of A, and then from the function, we can do our sketch. So I'm going to start is by, it doesn't matter what I start with. I'll start with K, I think. K is equal to 200,000. Like so. Now, if you wanted to, you could just make it 200 as long as your graph specifically said that it is in thousands of dollars. A is equal to, now it's 17% growth. So that means that the next figure would be 117%. Okay, so that's going to be 0 plus 0.17. Now, if you want to, on the side here for your notes, you might want to write 100% plus 17% if you think you need to know where those numbers come from. So that's it. And again, you could just do this in one step. A equals 1.17 would be fine. So 1.17 is the growth. So therefore, and now I'm just going to use, rather than using Y and X, I'm just going to use variables that probably represent the figures a bit more. So A for amount, big A, of course. I can't use a little a because that's going to be, that'll be confusing with the little a that we use. A is equal to K times A to the power of, and I'm going to use T for time. There we go. So I've got my function. Now I'm going to sketch it. I'm going to try and squeeze the sketching into the bottom of the left-hand slide there, so I can just use slide 12 for the graph itself. So I'm going to go through the steps. Number 1, y-intercept is 0, k. So it's 0, oh, sorry, I should have done shape first. Beg your pardon. Shape, growth, y-intercept is 0, 200,000. And one other point, when t is equal to 1, A is equal to 200,000 times 1.17, which equals 234,000. Yes, I worked it out earlier. I don't know that off the top of my head. Okay, so there's my 3 main points, or my 3 main bits of information I need. Shape, it's growth. Number 2, y-intercept is at 200,000. Number 3, one other point, when t equals 1, A equals 234,000. If I've remembered my numbers right, that's top of my head from when I worked it out before. Graph. Using a ruler like I have, A versus T, or T versus A. So I'm not using Y and X. Label 200,000 here. Draw in my growth. Oops, that's a bit too steep. Like so, because I know it's growth. And 234,000 is here. So again, that extra point just gives me perspective. I know that after 1 unit of time, 1 year in this case, there's not going to be a lot of growth, and so that's how I can see that on my graph. Without that extra point, it's a bit difficult to work out exactly how much is happening. Now, what have I missed from this graph quite deliberately? Yeah, the negatives. So because in this particular real world model, it doesn't make sense to talk about the year before I purchased it, I don't think it makes sense, then you can't really talk about negative values for t. And so t is constrained to being equal to 0 or above. So you just need to think about the real world application. I reckon 90% of the time, it doesn't make sense to talk about negatives, but sometimes it does. Like I said, with this population model on the board here, it does kind of make sense. Okay, questions, and then I'll set you to work for the last 10 minutes and then on to the next lesson. Jim.
If you were speculating in theory to calculate what it would be next year, you wouldn't know unless you've seen the growth before the years.
If I was speculating in theory what the growth would be in the year before?
No, you wouldn't know how to calculate the year after if you hadn't had any evidence of how much it had grown the year before.
Right, yeah. So you'd either have to have some sort of historical evidence to know what the growth rate was. In this case, it's given to you in the question, so it's artificial from that perspective. So if you think about things like climate change modeling and stuff like that, what they do is they look at historical data to determine what's going on. They come up with then a growth or decay figure based upon the historical data, and then their graph is based upon those assumptions. But again, Jem, as I've mentioned before, modeling functions in mathematics is only as good. Your function is only as good as the assumptions that underline that model. So, in a classroom situation, the assumptions are that what we're given in the question is correct. But in real world, it's like looking at historical data and saying, well, is this likely to be the same in the future, and that kind of stuff. Okay, so that's basically it. Oh, sorry, yeah. So if I then go to Desmos, which won't appear in the video, but you can see in Desmos, I've just simply gone A equals 200,000 bracket 1.17 to the power of t, and you can sort of see that I've got this sort of exponential growth graph cutting through at 200,000 as you would expect. So it wouldn't hurt for you to do a Desmos Desmos check of your solutions. Okay, I will shut up. What you need to do now is go to exercise 3J and do question 4. I've just done A, so do B towards the end. If you finish that, I've got a little bit more work that you can do, but I'll write that up on AirSketch so you've got it available. I'll just stop the recording and then we're done.